Welcome back. The purpose of this video is to clarify some terminology around data analytics, starting with what we call data. Now, it may be obvious to many of us what data is, but it helps to have a clear idea of what data analysts mean by this term. This is useful when picking your battles, essentially. In an arbitrary conversation about data, we tend to know whether we should get involved, and and that's why we need to have a clear idea of what data is for us as data analysts and how people are likely to use this term in different ways in the industry in general or specifically in a given project. Well, to start with, the dictionary definition is useful. Again, this will be obvious to many of us, and as we get more and more experience with data, it becomes more and more obvious. But in the interest of catering to all audiences, let's go through this slide anyway. So data is a noun, it's a plural noun, the singular being datum, which means that it is factual information such as measurements or statistics used as a basis for reasoning, discussion, or calculation. It is information in its digital form that can be transmitted and processed. Specifically, data is also irrelevant or redundant information that must be processed to be meaningful. Now let's keep that at the back of our heads before we proceed. Before we proceed, let's take a quick detour. In the analytics space, the last 10 to 15 years have been all about big data. This is a phrase that you will see a lot in advertisements, job postings, tech evangelism, many other places. My point here is to show you what big data means. For a beginner in this field who has just started to learn data analytics, it can be intimidating to hear words like big data analytics. Well, I'm here to tell you what it means. It means nothing really. Yes, you heard that right. Big data means nothing. There's nothing more about big data problems or big data technology or big data analytics that is new. All of it has existed for ages, well before big data as a phrase became popular. It's just that some specific analytical problems and technologies required to solve these problems are being packaged under the collective term of big data. Big data simply means distributed computing. Whenever you realize that your computational task is not going to be completed on a single computer and you have to resort to distributed computing, you are dealing with big data. There are two key resources on your computer, memory and processing. Whenever you have an analytical task that requires more memory or more processing than you have available on your single computer, you basically use big data techniques to solve that problem. And that's about it. All big data problems are problems of distributed computing, and all data algorithms and big data distributed algorithms. That's pretty much all there is to it. To reiterate, just like it is important to understand what data is, it is important to understand what big data is. Remember that the industry is in a perpetual big data problem. There will always be more data than we can analyze. Now, one of the reasons why big data scenario even exists is because of something called Moore's law. Moore's law, coined by Gordon Moore, who's a co-founder of Intel, says that the number of transistors in a dense integrated circuit doubles every 2 years. What this means is that the processing power of a given CPU chip more or less doubles every year. Also, note that transistors can also store data. So increasing the number of transistors on a chip increases its capacity to collect and store data. So basically, we are getting more and more on-device memory and more computing capacity as well. And I'm sure you have seen examples of this in your day-to-day lives. For example, the first computer I had was in the year 2000. It had a RAM of 128 megabytes. Today, I have a computer that has 32 gigabytes of RAM. That's an increase by a factor of 150 in just about 20 years. And that's a lot cheaper also. We can also see how broadband internet rates have decreased and how mobile data is getting so cheap that it's almost free nowadays. A little footnote here though, even though this is called Moore's law, it's not actually a law of nature or a law of physics. It's a statistically observed fact. This increasing trend that we see over here is because Intel and a lot of other companies chose to invest in semiconductor research and boost it as much as they could. That's why this is Moore's law as it was originally stated. The doubling factor and the time period of 2 years, both these factors keep changing from time to time. It's not a strictly straight line as you see here, but overall, in summary, this is why we have so much data and not enough analysts to go through that data. Well, now that we know what data is and why we have so much of it, let's take a look at the life cycle of data. Broadly, I've divided into four stages: generation, acquisition, analysis, and consumption. Note that these four stages may not be clearly demarcated in the real world, but it's useful mental model to have. For a given application, for a given client, for a specific industry problem, you can come up with your own model. But do have a model. It's important because it helps us decide at what stage an intervention is required, at what stage of the cycle action is required, and who should take that action. So let's go through this pipeline. So who creates data? Well, everything around you creates data. Nature creates data. The earliest uses of data analysis, which go all the way back to the age of enlightenment or the Renaissance period, were all about understanding natural phenomena. Many predictive and analytical models that we have today have descended from models that were used to model natural phenomena, like predicting floods on major rivers, or trying to predict when a volcano or a geyser is likely to erupt. A lot of early work in astronomy, from Copernicus to Newton, was based on data captured by sailors who would travel all over the world and try to record the movements and positions of stars and planets. Secondly, people create a lot of data. Just think of how much WhatsApp data you have generated in the last 24 hours, or how many emails you have sent or videos you have seen. Finally, machines themselves generate a lot of data. Well, machines are everywhere, obviously, specifically computers are everywhere. And computers act as central nodes which connect the internet, the information superhighway. So naturally, they generate a lot of information. Server log analysis is a favorite use case in data analysis, for example. Who collects this data? Well, individuals and organizations collect all of this data. Whether you like it or not, Google, Facebook, Amazon, many other organizations are collecting data, even if it may be anonymized. In particular, anybody who sells a service that needs data has a very good claim on the data that it collects. For example, I have a blog, and it would be very wasteful if I did not collect the data on likes, shares, views, or comments on my blog. In general, it's a good practice to set up a data acquisition framework ethically before you launch a service or a product. You don't want to be caught into some controversy only later to surrender all your data. Now, this is where things get a little practical. Who analyzes data? Well, pretty much everyone. My grandmother used to do it, just that she did not know how to use spreadsheets. All of these people are your potential clients. And finally, the consumption is the single most important aspect of the pipeline. In fact, I'd say that this is more important than the analysis itself. We will motivate this further in an upcoming video, but there is absolutely no shortage of analysis. But there is a massive problem with the consumption of that analysis. Let's think about it. If you are somebody who has a smartphone, there will be apps on your phone that will be doing some sort of automatic analysis. For example, Google Maps sends an automated email every month telling you how many kilometers you have traveled, which places you have been to, etc. A Fitbit might record all your physical activity, but we as consumers have no idea what to do with all of this data. For example, if I were to develop health problems later in my life, I would have to change my exercise routine. But I would conveniently forget that I had data lying on my Fitbit device for years and I did nothing with it. This, unfortunately, is what goes wrong with many of us. First, something goes wrong, and only then we realize that there was some data which was giving us all sorts of hints about an impending problem. And this is what I mean by inefficient consumption. Doing analysis is the easy part. making it stick, making people listen, that is where you make an impact. And these are the two stages that we are going to focus on throughout this course. We are going to develop a framework for doing analysis and then making sure that it properly sinks its teeth into the consumer. Before we conclude, let's come down to the brass tacks. In this course, we are going to deal with data sets, which are basically pieces of data that are present as tables. We are not going to discuss databases, data streams, or unstructured or real-time data. If some data is not present as a table, we are not going to deal with it in this course. That's because to deal with data in all its varieties and forms, we need to invest some time in data engineering, which is, well, fairly out of the scope for this particular module. But that doesn't mean that dealing with individual tables is a limitation. In fact, that is the most common way of storing and sharing data. Clients are more likely to share individual files with you rather than give you access to their database servers, for example. When sharing data, we are more likely to upload individual files on the web. In short, we are going to deal with small data exclusively. And as we shall see, doing good analytics on small data itself is half the battle won. The rest is just engineering and automation. So we will be dealing with individual data sets. Each data set will be a table, that is a two-dimensional data structure, something that has rows and columns. Each row represents an object of a given type, and each column would represent one attribute of the objects. Then if you take the object and one of its attributes, for each such pair, you will get a cell which contains some measurement of that attribute for that object. Here's an example. This is a very famous data set called the Fisher Iris dataset. Many of you might have already seen this dataset. It contains 150 rows which correspond to 150 samples of the iris flowers, each row being one flower. It has 5 columns, as you can see, which means that for each flower we are taking 5 different measurements. These measurements are the lengths and widths of the petal and the length and width of the sepal. FYI, the sepal is the pod that encloses the flower before it blooms. Once the flower blooms, the pod breaks and the broken pieces of the pod which stick to the stem of the flower, they are called the sepal. We also have the species of each sample over here. In this data set, there are 3 unique species. That is, each sample belongs to 1 out of 3 species. To reiterate, the whole table represents a collection of objects of the same type. In this case, the objects are individual sample flowers. Each column represents one attribute of the object. In this case, we have 4 physical measurements and 1 other attribute. Each cell value is the measurement for the corresponding object and the attribute. All the data sets we will use in this course will follow the same semantic structure. Tables, rows, columns, each of which has a precise meaning. So this is what data means for us.